This is the first lecture series that will be focusing on acids and bases. We're going to talk about some of the definitions that allow you to identify a substance as either being acidic or basic. And as you'll find out in not only this lecture, but future lectures, we're going to look at some of the calculations associated with finding out the concentrations of acids and bases in something known as the pH. But let's start first by looking at the individual definitions of what it means to be an acid and a base. And there are different ways of looking at these substances that explain the substances, but the extent to which they can explain, the full context and the full definition of the acid cannot differ. So we're going to start with the Arrhenius definition, which is the most simplistic. From the point of view of Arrhenius, an acidic substance is one that contains hydrogen, right? Specifically, when you write the formula of the molecules, the hydrogen is the first element present in the formula, and then there is something else. This could be a binary acid or it could be a polyatomic acid. But the idea is that you have an H present in there, an H that can be donated or that can be used to generate H pluses in solution. But the idea is that Arrhenius looks at the molecule, the reactant, and says, oh, this has an H in there. This could be an acid. So anything that can produce that H plus technically is what an acidic substance will be denominated as based on the Arrhenius definition. And one thing that we're going to be using in a little bit is the pH scale. So I'm going to tell you right now that the pH is actually a function. Specifically, P is a function and H kind of takes the role of X. So this is kind of like f of X, where f is the function negative log. X is what goes inside the log, right? So we have pH is the negative log of H plus concentration. Another way to also depict this is as hydronium. This is the more proper way of looking at H plus, because H plus is simply a naked proton. But in solution, in water, the proton is not going to be by itself. It's actually going to be mixing together and kind of teaming up with the molecules around it, which in this case will be water. So if you add a water to this H plus, you end up with H3O plus, which is known as hydronium. But it's the same idea. Concentration of hydronium or concentration of H plus, it's literally the same thing. All right, now from the point of view of Arrhenius, a base is a molecule that contains OH or hydroxide. Okay, so specifically these are ionic substances where E stands for a metal, and as long as you produce the hydroxide, you are considered a base from the point of view of Arrhenius, right? And much like the pH, we could also look at something known as the POH. And once again, H or OH are basically taking the role of X in this f of X function, right? So we still have the negative log, but instead of taking the negative log of hydronium, now we take the negative log of hydroxide, and that leads to the POH. Eventually, I'm going to show you how the POH and pH relate to one another and the full scope of the calculations that we can enact with those values. But for now, just going to be aware of that negative log relationship for pH and POH. All right, so anything that generates H plus, anything that generates hydroxide, from the point of view of Arrhenius, gives you an acidic substance or a basic substance. But the issue with that is that there's a lot of other substances out there that don't quite necessarily fit that definition, and yet they behave like an acid or a base. So here enter Bronsted and Lowry. All right, so Bronsted-Lowry, the two fellas, shown here, left and right, apparently, they got him on a bad day because they did not want to, they did not want their picture taken that day. At least that's what I can surmise from the look on their faces. But pretty much what they do is they look at the substances from a different perspective. In terms of acids, instead of looking at what the particular substance contains within it, they focus on what it produces. And here definitely they look at the fact that the molecule has to donate an H plus for it to be considered an acid. And simply stated, that's almost the same thing as saying the initial substance has to have an H to begin with. So from that point of view, the Bronsted-Lowry definition of an acid doesn't really add anything extra to the picture than the Arrhenius definition did. But where the Bronsted-Lowry definition shines is with the bases. I'm going to get to that in a second. Before I do that, I want to highlight a few assets that I want you to remember as being strong. And it's basically a list of 9 assets, 11 assets, but it's not as bad as it sounds because, as you can see here, if you remember HCl, HBr, and HI, so hydrochloric, hydrobromic, and hydroiodic acids, all you have to do is add 4 extra oxygens or 3 extra oxygens to the hydrohalic acid to derive the other 6. So you have hydrochloric, perchloric, and chloric, the same way you have hydrobromic, perbromic, and bromic, or hydroiodic with periodic and iodic acids. All of 9 of those are strong acids. And in addition to them, we also have you remember that sulfuric acid and nitric acid are strong acids. It's kind of important that you remember these 11 assets as being strong because most any other acid that I'm gonna throw in your direction or show you or analyze is going to be regarded as weak if it's not one of the 11 shown in here. So for instance, if I show you HF or bromose acid or ascorbic acid or citric acid or any other acid other than the 11 ones that I showed you in the previous slide, any of these acids are going to be regarded as being weak. So that's the idea. Remember these 11 so that you can identify something as being weak or strong. As of now, that may not play a huge role, but we're going to get to the section where we're actually doing calculations and you're trying to identify things, specifically the pH, how it's going to change, and the recognition as to whether you're dealing with a strong acid versus a weak acid will make the difference as to what approach you take in calculating the pH of a solution. All right, now, as I was saying earlier, the Bronsted-Lowry definition doesn't shine when it comes down to the acidic substances. Pretty much it's the same definition as the Arrhenius definition. But where it does definitely shine is with the bases, because instead of looking at it from the point of view of producing hydroxide, the Bronsted-Lowry definition still obsesses with the protons, okay, the H pluses. And so for the acids, they said, okay, anything that produces H plus, that's an acid. On the other hand, anything that reacts with an H plus, anything that takes up that H plus is a base. So in doing so, they actually extend and expand the definition of what it means to be a base. Because yes, hydroxides can react with H plus to give you water, and that happens. And fine, that still qualifies hydroxide as being a base. We haven't changed that whatsoever. But what it does do is that it introduces anything else that can react with H plus as a base. And one way to look at it too is that anything that has lone pairs could potentially be reacting as a base because the H plus is a naked proton, so it needs to have electrons attacking it to be taken up into some other molecule. So this expands the list quite a bit. So carbonates, hydrogen carbonates, phosphates, sulfides, oxides, pretty much things with lone pairs are possible species that can react as a base. So this really broadens up the scope of what we can think of being a basic substance. So another thing that we're actually going to do a lot when it comes down to acids and bases is derive balanced equations. Balanced equations that involve water, right? So for instance, you have a substance A minus, which is a base. If you add that base to water, or to put it simply, if you make a solution of this base in water, the base can react with water to some extent. And because A is a base, it will be taken up an H, right? So you go from A minus to HA, and the water that lost its H plus, now it's hydroxide. So this is going to be a common feature. Basically, one substance takes an H plus, the other substance loses an H plus. All right, now some typical examples of bases. The ones that I have highlighted on the red box are the typical strong bases that we tend to use in the lab. Most likely not, we're going to be talking about alkali metal hydroxides like sodium hydroxide, lithium hydroxide, potassium hydroxide. Those are your typical strong bases. But there's a few extra that I'm putting in here just for your information, like lithium sulfide, sodium oxide, sodium sulfide, lithium oxide. Those things are definitely strong as well. Uh, and if you don't have a hydroxide or oxide salt, it's very likely that your base is going to be weak. In fact, let me put it to you this way. If you don't have that alkali metal present in there, it's very likely that your base may be weak. One that I definitely need you to remember is ammonia. NH3 has that lone pair which can actually act to remove H pluses from other substances. That is a base, but it is a weak base. And technically speaking, adenine, right, which is part of DNA, is technically a base. And you can see that clearly because you have a bunch of nitrogens that do have lone pairs. And it's those basic properties ultimately that allow adenine to retain the double helix shape of DNA. Alright, so we're going to stop the video right here, and on the next video we're going to talk about water and the equilibrium constants associated with acidic and basic reactions, which are known as the Ka and Kb constants. So I'll see you in the next video.